All right, chapter 9. So we're going to talk about probability today, and we've already technically done a little bit of this, but this is going to be your more general form of probability and not your statistical analysis for normal distribution, or what we're going to do in chapter 10, which is sampling distribution. Anyway, we're going to do chapters 9 and 10, and then I'm going to give a quiz. Okay, then chapters 13 and 14, and that'll be it. So we're going to get started. A probability is a science of chance. A chance behavior is unpredictable in the short run, but has regular and predictable pattern in the long run. So we can never really use probability to predict outcomes or statistics to predict outcomes or immediate outcomes. Okay, but long-term behavior we can. This is why we can use probability to gain useful results from random samples and randomized comparative experiments. The randomness and probability, random and individual outcomes are uncertain, but there's a regular distribution of outcomes in a large number of repetitions. And relative frequency of the proportion of occurrences of an outcome settles down to one value over a long run. That one value is then defined to be the probability of the outcome. So, example would be if you flip a coin, let's say 10 times, you know the probability of getting heads is 50-50. Okay, 50% of the time you're going to get heads. But it doesn't mean that if you flip a coin 10 times, you're going to get 5 heads and 5 tails. But if you repeat the event, you repeat it enough, so if you repeat it 100 times or 1,000 times or 10,000 times, you're going to get closer and closer and closer to the what they call theoretical probability of the outcome. All right, so relative frequency probabilities can be determined or checked by observing a long series of independent trials. Like I said, you can repeat the events enough, you get accurate data. This is the flipping coin question. That's why I kind of brought it up. Now, probability models. Here's some things you want to write down. Sample space S, that's usually the symbol we use for sample space, of a random phenomenon is the set of all possible outcomes. So, for example, if you're rolling a die, just one standard 6-sided die, your sample space S is the set of 1, 2, 3, 4, 5, 6. So those are your outcomes, right? Let's say you have 2 children. You have actually 4 different outcomes with the gender of 2 children, and we're just going to assume from birth, male, female. Okay, so you can have 2 boys, so boy, boy, 2 girls, girl, girl, and you can have a boy, then a girl, or girl, then a boy. This would also begin your sample space. This is the list of all possible outcomes, right? An event is an outcome or a set of outcomes, which is a subset of the sample space. For example, if we're rolling a die, an event can be, oh, I did 2 E's there. An event could be rolling an odd number, okay? Or if you're dealing with, like, say, the children, your event could be at least 1 girl. Okay, so those could be a sample set. It's a sample space. It's a subset of your sample space. Okay, so your odds would be 1, 3, and 5. At least 1 girl would be girl, boy, boy, girl, or girl, girl. Okay, so these are subsets of your sample space. A probability model is a mathematical description of the long-run regularity of the sample space. So it gives us a way of assigning probabilities. So let's go back to rolling a die. Okay, here's your outcomes rolling a die. What's the probability of getting any number when you roll a die? Okay, so the probability of your sample space would be 1 out of 6, 1 out of 6, 6 out of 6, 1 out of 6, and 1 out of 6 because let's assume it's a fair-sided die. So each outcome, there's 6 outcomes. Each outcome is an individual, so 1 out of 6 outcomes possible. So that's your probability model. Now you could have an unfair die, so probability from an unfair die, okay, where you may have a 1 in 12 probability of getting a 1, and a 1 in 3 probability of getting a 2, and a 1 in 6 probability of getting a 3. So another 1 in 12 probability, and then another a 1 in 4 probability, 1 in 12 probability. If you add this up, the big thing about this, and you're going to see this in another slide, is that if you add all this up, you should get a sum of 1. So if you add all these 1/6 up, you get 1. If you add this up, you're going to get 1 out of 12 plus 4 out of 12, because that's 1/3 is 4 out of 12, plus 2 out of 12, that's 1/6, plus 1 out of 12, plus 3 out of 12, plus 1 out of 12. This gives you 1, 5, 7, 8, 11, 12. So 12 out of 12. There we go. Here is a sample space for rolling 2 die, and there's actually 36 outcomes. Now, again, it's hard to see because sometimes, it's hard to see when you have 2 die, especially if they're the same color, because if you roll a 2 and a 1, is that the same thing as rolling a 1 and a 2? Well, if they're different color die, it's a little bit easier to see. Okay, so there's a difference between rolling a blue 2 okay, and a blue 1. Okay, so there's the difference. Is if this is white and this is blue, then it's a little bit more obvious that the outcome is different. And sorry, I'm just not going to color in the whole thing. Okay. So blue die is 2, white die is 1, or blue die is 1, the white die is 2. There's separate outcomes. It is a little bit easier if you see it like that. Okay. But there's 36 total outcomes of rolling 2 die, and each outcome is equally likelihood 1 out of 36. Okay. All right. Now here's some big probability rules. Number 1, there is no probability that's negative, and there's no probability greater than 1. All probabilities must be between 0 and 1. Now, if it's 0, if you have a probability, let's just use probability of A. It stands for probability of A. Equals 0, this is called 0, an impossible event. Right? If your probability B is equal to 1, this is called a certain event. Anytime your probability, we'll say of C, is less than 0.5, this is called a unlikely event, I think. Okay, it's still possible. Say less than, 0.05, so less than 5%. Okay, an unlikely event. Okay. Probably can be interpreted. All right, fine. That's probably number 1. Is everything must be between 0 and 1. It can equal 0, it can equal 1, but it cannot be below 0 or above 1. Rule number 2, the sum of a probability distribution, okay, of a sample space. Some of all probabilities of a sample space must add up to 1. Okay. Now I'm going to show you an example of that somewhere. Where is it? There it is. So this right here, where is it? Here we go. This right here is called a probability distribution, where we have this. This looks up tax records, basically anything involving where your file is numbered. A file is numbered instead of named. The probability of the first digit being a 1 is about 30%, a 2 being 17%, 3 being 12.5%, and so on and so forth. So it seems to be less likely further down the road. Now, first thing you have to do is make sure this is a proper probability distribution, which means you would want to add up every one of these. So add, right? So you would want to add all this up together, and it should equal 1. That's really the only thing you have to do, because the other rule is that none of these can be bigger than 1, which is kind of obvious. You look at all the numbers, they're not bigger than 1. And none of these can be less than 0, and again, also obvious because nothing is negative. So there we go. The big thing, and those should be obvious, but the rule that you're going to actually have to check is you're going to add up all the probabilities, and it should add up to 1. Okay, so that's what that rule stands for. All right. Let's see, probability rule 3. All right. If you have two separate events, okay, for example, let's say you roll a die and then you draw a card, okay, the events are considered, no, sorry, I'm thinking of something else. If you have two events that have no shared outcomes, they are considered disjoint. Another word for this, right? Another word for disjoint is, where's my mouse? Mutually exclusive. Again, just means no shared outcomes. All right. So for example, if I was looking up the probability, let's say I'm picking a deck of cards. It's always a good one to do. Picking a club. Okay, which again, if you don't know cards, you can look up a deck of cards online. Picking a club, okay, or a red card. Right. Now, since a club is a black card, there's no way that these could overlap. So these are disjoint events. Okay, or mutually exclusive. I like the phrase mutually exclusive just because it's a little more intelligent than disjoint. And to me, a little more accurate than disjoint. But there are no overlapping outcomes. A club, it can never be a red card, and a red card can never be a club. So this would be disjoint. Now, another example is if you have, let's say, the probability of picking a club or a 7. Is there a 7 that is also a club? Yeah, there's a 7 of clubs. So these are not disjoint. Okay, are not mutually exclusive. Okay, not mutually exclusive events. Okay. So probability, if two events have no outcomes in common, they're said to be disjoint. The probability that one or the other two disjoint events is the sum of the individual probabilities. Right. So here we go. Right, here we go. Right. So here we have the age of a woman when their first child is born. Under 20 is 25%. 20 to 24, 33%. So if we said, what's the probability of the age of a woman, first child's born, is under 24, well, under 20 or 20 to 24, since there's no way you can be under 20 and 20 to 24, there's no way to be that age, okay? These would be disjoint events, and we just add these together. You would get 58%. So that's the rule. If you have disjoint events and you want to find the probability of one or the other, you would just add these two together. Okay. Clear. Probability rule 4, the probability that an event does not occur is 1 minus the probability it does occur. This is called the complement rule. Write this out. Complement rule. Usually denoted as the probability of that, which means complement of A. Or 1 minus the probability of A. Okay. So for example, let's say you have a 1 in 4 chance of picking a club card. Then 1 minus 1 in 4, which is 3/4 chance, is the probability of not picking a club card. Okay, so that is the complement rule. It's 1 minus the probability that it does occur. So probability of something not occurring is 1 minus the probability that it does occur. Okay. Here are the probability rules written more in an algebraic sense, or more how I would like it to be seen. Feel free to pause and write this down. Okay, the probability of an event must be between 0 and 1. It could be equal to 0, it could be equal to 1, right? The sum of all the sum of probability model, okay, must add up to 1. If two events are disjoint and they have no outcomes in common, the probability of one or the other occurring is the sum of the two probabilities, two separate probabilities. And the complement rule, probably something does not occur, is 1 minus probability it does occur. That's all the rules. Anything else? Oh, notation again. I already mentioned notation. Probability of rolling a 5. That means probably rolling a 1 and a 4, a 3 and a 2, a 2 and a 3, or 4 and 1. So you'd add up these separate probabilities. 1 and 36 probability each, so add them up. 4 to 36, which always reduce your fractions. 1 out of 9. Okay. Discrete probability. Now, discrete probability means there's a finite or countable measure of outcomes. Okay, for example, if I went around my neighborhood and I surveyed how many cars people had in their driveway, I would have to count them. Okay? I would have to count them. Now, if I wanted to survey how big their front yard was, I would have to measure that. So if it's counted, it is a discrete probability. Okay? Continuous probability is a measured. Okay, it cannot be assigned a probability to each individual outcome because there's an infinite number of outcomes. Right? Probabilities are assigned to be intervals of outcomes by using areas under a density curve. So this is what we're going to talk about when we do sampling distribution, and we've already kind of done this with normal distributions back in chapter 3. If you remember finding probability or proportion of an event, that's what this is. Okay, finding your z-score, find the probability between two values, less than a value or greater than a value, stuff like that. You're not going to do any of this, so we're on. Normal probability models, we did this back in chapter 3. Okay. And we're going to use Google Classroom to do all this anyway. Okay, so valuable, not important. Okay. Important. Okay, that's it. Okay, so what I want to do now is go over some of the practice questions. I'm going to go all the way back up here, make sure we're comfortable with some of these questions. Starting with 9.1. And this is just explaining what this means, what this probability means. So a straight in poker is a hand of 5 cards whose ranks are consecutive when you arrange them in order, such as 8, 9, 10, Jack, Queen. Read a book in poker, the probability of being dealt straight is 4 out of 1,000. Carefully explain what this means. Okay, so you have a couple ways to say this. One, you can use the numbers they give you, or you can reduce the fraction. If you play, poker 250 times, because if you reduce this, you get 1 out of 250 times. You have a high probability of getting at least 1 straight. Okay. So you should get at least 1 straight out of every 250 games of poker. It doesn't mean you're going to, but that's the theoretical probability of it occurring. Okay. 3 of a kind, I think same question, so as I said, again, that's the probability of it occurring. That doesn't mean exactly, because again, this is theoretical. This is not, the short-term rule does not apply. That's really about all the same question. It's basically saying short-term probability does not apply here. And these are actually wanting you to do experiments, and I'm not going to have you do any experiments, so I'm not going to do any of 9.3 or 9.4 because they want you to do all this. I'm assuming you don't have thumbtacks at the house. Because who does? Right? Alright, let's see here. Not going to worry about that. Not going to do experiments. Okay, let's look at this one. Probability is a measure of how likely an event is occur. Match one of the probabilities that follow the statement of a likelihood event. The probability is usually a more exact measure of likelihood than it's a verbal statement. So this event is impossible. It can never occur. That's 0. Okay, so I'm going to write on here. This event cannot happen. So that probability is 0. Okay, this event is certain. Will occur every trial. That's 1. I've already mentioned certain event and impossible event. Is very unlikely, but it will occur every once in a while. So that's the most unlikely event, 0.01. It's unlikely. Okay, it doesn't occur more often than not. You could say definitely this one. Okay, but yeah, either one of these be fine. Okay, so there we go. For 9. That 0.7. All right, so we talked about probability models, the rules about probability models. All right, so let's look at some questions. So here we go. Choose a student at random from large. Okay, we can't do that because we don't have class. Okay, we're going to. Okay, here we go. Sample space. Each of the following situations describe the sample space from the random phenomena. A basketball player shoots 4 free throws. You record the sequence of hits and misses. So here's the thing: when you shoot, you're either going to make it or you're going to miss it. Okay, so what you may want to do anytime you have 2 outcomes is called a binomial distribution. Okay, where you only have 2 outcomes, either a hit, where again it goes in or out. So we'll say hit or miss right now. Okay, and that's from the first free throw. That's free throw 1. Let me do this in a different color so we can see it as we go down. So you're either going to make it, hit it, or you're going to miss it. That's your first shot. Now the second shot. What do you say? Just a second. Okay, sorry, I had to take care of something. Okay, so the second shot you're either going to, again, hit or miss, depending on what happened the first time. You could hit the first one and the second one, hit the first one, miss the second, miss the first one, hit the second, miss the first one, miss the second. And then there's the third shot, which you also hit, miss, hit, miss, hit, miss, hit, miss. I don't know if you see where we're going. This is called a tree diagram, where you kind of just keep going down, 4-shot, hit or miss. So you have 16 total outcomes here. You could hit all 4 times, make it in all 4 times, 100% free throw. You could hit 3 times in a row and miss the last one. So that is, this one would be hit all 4. This is hit the 3 and then miss the last one. Hit 2, miss 1, then hit the third. Hit 2, miss 1, hit the third. Or you can hit 2 and then miss 2. So that takes care of these 2. Then you can hit 1, miss, and then hit the last 2. Hit 1, miss, hit another, miss. Hit 1, miss twice in a row, and then hit the last one. And then hit 1 and then miss the rest. So that takes care of basically all of these right here, going down the factoring tree. Then starting here, miss, hit, hit, hit. So you can miss the first and then hit the next 3. Or you can miss the first, hit the 2, and then miss the last. All right, miss the first, hit, miss, hit, hit. No, miss, hit, or miss, hit, miss. Or you could miss the first 2, and then hit the last one, hit last 2. Miss the first 2, hit the third, miss the last. Miss the first 2, miss the first 3, and hit the last one, or miss all 4 of them. That's all 16 different outcomes. This is the sample space. This is how you would record all the outcomes. That's your sample space, right? Now, what if it says the basketball player shoots 4 free throws and you record the number of baskets he makes? That's a lot easier, because either he's going to miss all of them, he makes 1 of them, doesn't matter which one he makes, because you just say he recorded how many he makes, it only makes 1. He makes 2 of them, makes 3 of them, or makes all 4 of them. So you're not really worried about the order of the events, just how many they make out of the 4 attempts. That's a lot easier. Okay. All right, clear that. Each describes sample space. So, study of healthy adults measures the weight of adult women. Well, that could be a lot of different things here, right? That's going to be, yeah, freedom specifying sample space. I'm not even going to specify that. Okay. So here they asked 11,000 patients, a physician, take an aspirin every day and observe how many of them had a heart attack in a 5-year period. So that sample space could be 1 to 11,000. Or 0 to 11,000. None of them had a heart attack over a 5-year period. Test new package design. You drop a carton of a dozen eggs from a height of 1 foot and count the number of eggs broken. So that sample space is going to be from 0 to 12. Okay. All right. Moving on. So questions. Okay. Rolling a saw 4. Saw 4, rolling a dice, 2 dice. Roll a 1 on one die and a 3 on the other. If you roll 2 dice, what's the problem rolling a saw 4 or rolling a 4? Alright, so this is 2 dice. Now again, you have to remember, you can reverse the order of the dice. So you can roll a 1 and then a 4. Sorry, a 1 then a 3. Or a 3 and then a 1. So you have 2 outcomes out of the 36. So 2 out of 36 outcomes are 1 out of 18, and feel free to just leave it as a fraction. 1 out of 18. Okay, we're rolling a soft 4. Okay, I don't know why we got too far from the outcome. So soft 4. Okay, now the difference between rolling a soft 4 or a 4 is you can include 2 2s. And again, you can't really reverse the order because they're the same number. So you have a 3 out of 36 outcome or 1 out of 12 for rolling just a 4. Okay, that's number 911. The company offers a course to prepare would-be MBA students to the Graduate Management Admission Test, GMATs, as the following information about its customers. 20% are currently undergrad students in business, 15 are undergrad students in fields, 60 are college graduates who are currently employed, and 5% are college graduates who are not employed. Is this a legitimate assignment of probabilities to customer backgrounds, and why? What you want to do is add this up. 20 plus 15 is 35, plus 60 is 95, plus 5 is 100. It adds up to 100%, or it adds up to 1. Yes, it's a legitimate assignment of probabilities. What percent of customers are currently undergraduates? So undergraduate in business, undergraduate in other fields. So you'd add these two. So 35% are undergraduates. Because again, you can't be an undergrad in business and another field. You're usually going to be one or the other. So that you just add together their disjoint events, 35%. Okay. All right. What happens to trees over a 5-year period? A study lasting for more than 30 years found the probabilities for a randomly chosen 12-inch diameter tree in the Ozark Highlands, Missouri stay in the 12-inch class 0.686, move to the 14-inch class 0.256. What's the remaining trees die during the 5-year period? What's the probability that trees die? So basically what's left? Either they do this or they die. So we basically just do 1 minus these. I'm going to add these together first because these don't overlap. So I'm going to add 0.686 and 0.256. 12, carry the 1, 14, carry the 1, 0.942. So 1.000 minus 0.942 is 8, 5, yeah. So 0.058, or a little bit over 5% die within the 5-year period. Else. I'm not going to do doing this. I'm not going to give you any questions that do it way. There. No problem. I may give you these questions because we'll go back to how to do these in a bit. Okay, so I'll have to go back to Google Sheets so you can do these questions. All right. So if you remember, and let's go ahead. Oh, this one's actually pretty easy because you just, what's the probability of getting x less than 3? Okay, this we can do. If you're given a probability model, you can find this. How many numbers are less than or greater than or equal to 3? So that's 3 and 4 here. Okay, so that's going to be 3 and 4. So we just add those together. 0.50. What's the probability? 50%. Write the event the students got a grade poorer than a C in terms of, so how would I write poorer than a C since a B is 3 and an A is 4? Poorer than a C is less than a 2. So you can either write it as this. There's two ways to write it. That's the probability that X is less than 2. Or you could write it as the probability that X is less than or equal to 1. Because again, there's a limited number of outcomes here. Okay. This. All right. Example 9.6 describes the assignments of probabilities to 36 possible outcomes for tossing 2 die. Take the random variable x to be the sum of the values as they add up. So again, x is 5. That means there's 4 out of 36 ways to roll a 5. X is 7. There's 6 out of 36 ways to roll a 7. And again, you could use this chart that's up here, way up here. There, nope. There it is. You can use this chart to find all the different outcomes. Okay, so feel free to do that. It says, give the complete probability distribution of discrete random variable x. That is, list the possible values of x and say what the probability of each value is. Start from, no, I'm not going to do that. Okay, I wouldn't give you that question to begin with. Okay, this is the one where we need to find z and then do this on Google Sheets. Okay, so normal distribution. Anytime it says normal distribution, that means we use Google Sheet. Okay, so, and I'll go back to Google Sheets. In fact, let me go ahead and open this up. We did this already in chapter 3. I don't know if you remember chapter 3. It was a while ago. Here, Sheets. Link. All right. Nope, don't want to do that. So we know that mean mu is 6.8. Sigma, which is your standard deviation, is 1.6. And it says, if we use model, the score y of a random chosen student continuous, write the event the student chosen has a score of 10 or higher. Okay, so this is saying find the probability that x is basically greater than or equal to 10. All right. By the way, for continuous distribution, which is what this is, continuous distribution, the equal to doesn't matter. Greater than 10 and greater than or equal to 10 doesn't make a difference. Okay, they're the same thing. So we're going to say our random value here. So our x is 10. And if you remember, we did this formula, found z by using the equals round of let's just, I don't really need anything else. Let me clear this. Right, close that. I don't need it. So I'm going to be rounding the equation, which is, I'll write this on here. I want that. If you remember the equation for finding z, if you don't, here it is. Z is equal to x minus mu over sigma. Okay. So that's what I have to write here. So x is that, but I got to put it in parentheses. So it's going to be in parentheses, two parentheses, x minus mu, all right, close parentheses, divided by sigma. And then I always round z to 2 decimal places, so comma 2. All right, so again, let me copy and paste this here. Copy. Oh, F and B2. All right, so that's the formula. This is what you would type in Excel to find z. Okay, so, or not Excel. This is the we'll say the Cheats formula. Okay, so write down that formula. Okay, where B3 is x, B1 is mu, and B2 is sigma. As long as you put them in those positions, you're good to go. All right. Now, what I have to do to find, if you remember this, you may still remember this. Probability less and probability more. Okay, now in this case, we're trying to find greater than 10. So we want to find probability that x is greater than or equal to 10. And again, the equal to doesn't really matter. Greater than 10 is fine. So we want to find this. But it really is the same formula, if you remember. Right? It is equal to norm. There it is. No, not norm distribution. See? Might be norm S distribution. See? Yep, there you go. And we do want this rounded to 4 decimal places, so my answer would be 0.9772. Now, for probability more, that's equal to 1 minus norm dot S dot distribution. So let me copy this again. Okay. Now my final answer question would be my battery ran out. Yep, my battery just ran out. Yep. So my final answer would be, I'm going to try to use my mouse, 0.0, I'm just going to type this. I can't do this with my mouse. Would be 0.022, actually that'd be 228, because this would round. Okay, so that would be my answer there. This, I can't use my pen anymore, I might as well just put it away. I really think that's everything that we needed. We don't do anything personal probability. Okay, so here's the homework. I'm going to tell you what it is now, so you can just get started on doing this. I wrote this down. It is 9.26, 9.26, 9.27, 9.28, 9.29, ooh, too far, 9.29. Basically, I want to say it's just 9.26 all the way through 9.33, 9.33, and then you're going to skip some, because again, a lot of shit is, but I do want you 9.6, and then 9.8, 0.6, 9.8, okay, and then go down here to what we just did. Looks like you don't have any questions. The normal distribution. Okay, here we go. 9.41. Okay, so 9.41. I will post this on Google Classroom. Okay, so it is again 9.26. Basically, skip 9.25. 9.26 to 9.33, 9.36, 9.38, 9.41. And that is everything. That is all the homework for Chapter 9. We're going to move on to Chapter 10, which deals a little bit more of this normal distribution, and I'm pointing at the screen like you see anything. Deals a little bit more with this normal distribution, but we're dealing with sampling distribution, so there's one slight difference, not really much when it comes to doing the hard work of it. After that, we'll have a quiz. And then we're going to cover the last 2 chapters, and we'll be done. We'll have a test or a final. I don't know how, because from what I'm seeing and from what my wife is telling me, I don't know if we're coming back to school this semester. So I don't know how we're going to do any of this. I don't know how graduation's going to work. So I'm definitely getting in contact with everybody to see how that's going to work. Because, yeah, it's unfortunate. And it could be that just once everything gets back to normal, and it should, just going to take a while, they'll have a graduation ceremony for you guys. Okay, I guarantee they're going to have a graduation ceremony for you. Okay? Anyway, that's all I have. And I hope you have a good night. Stay safe. Wash your hands. Do your homework.